Vibration Analysis Rule 1, Advanced Vibration Concepts, Sine Waves, Beating, and Intermodulation, Exploring Complex Wave Interactions in Vibration Analysis. Sine wave characteristics, different amplitudes, same frequency, same amplitude, in phase, effects of phase, phase cancellation. When two sine waves of the same frequency but different amplitudes combine, the resulting waveform exhibits varying peak levels rather than uniform oscillations. This occurs because the larger amplitude dominates, creating a composite signal that fluctuates between the sum and difference of the two amplitudes. In practical terms, this means that the vibration pattern will not cancel out completely, and the machine may exhibit irregular vibration intensity. The spectrum analysis of such a waveform will reveal two distinct peaks corresponding to the original frequencies, with their heights proportional to the respective amplitudes. This concept is critical in machinery diagnostics because it explains why certain components may appear to contribute disproportionately to overall vibration levels. Understanding amplitude differences helps analysts identify which machine parts exert greater dynamic forces and prioritize corrective actions accordingly. When two sine waves share identical frequency and amplitude and are perfectly in phase, their combination results in constructive interference. The waveform becomes a single sine wave with double the amplitude of the individual signals. This phenomenon is common in rotating machinery where multiple forces act synchronously, such as coupled shafts or aligned components. In the frequency domain, the spectrum displays a single peak at the shared frequency, but with significantly higher amplitude, indicating increased vibration severity. This scenario is important for analysts because it demonstrates how synchronized forces can amplify vibration levels, potentially accelerating wear or causing structural fatigue. Recognizing in-phase conditions helps in diagnosing alignment issues or resonance phenomena, where components vibrate together harmoniously, leading to elevated stress on machine parts. Phase differences between two sine waves of the same frequency alter the shape of the combined waveform without changing its frequency content. As the phase shifts, the peaks and troughs of the waves slide relative to each other, creating patterns that range from constructive to destructive interference. While the time domain waveform may appear distorted, the spectrum remains unchanged because the frequency components are constant. This principle is vital in vibration analysis because phase relationships influence how forces interact within a machine. For example, phase shifts can indicate misalignment or looseness, where components move out of sync. Analysts use phase measurements to determine relative motion between machine parts, aiding in fault diagnosis and corrective alignment procedures. Phase cancellation occurs when two sine waves of equal amplitude and frequency are 180 degrees out of phase. In this condition, the positive peak of one wave coincides with the negative peak of the other, resulting in complete cancellation and a flatline waveform. In the spectrum, this manifests as the absence of a peak at that frequency, indicating that the combined effect of the two signals is zero. Although perfect cancellation is rare in real-world machinery, partial cancellation is common and can mask underlying issues. Understanding this concept is crucial for analysts because it explains why certain faults may not appear in vibration data despite being present. Phase cancellation can occur in systems with redundant components or opposing forces, making phase analysis an essential tool for accurate diagnostics. Nature of beating, spectrum analysis of beating, correcting beating. Beating occurs when two sine waves of similar but not identical frequencies combine, producing a waveform whose amplitude rises and falls periodically. This pulsating effect, known as the beat frequency, equals the difference between the two original frequencies. In machinery, beating often manifests as a droning or throbbing sound and can lead to fluctuating vibration levels that stress components intermittently. The phenomenon is common when two machines operate at nearly the same speed or when looseness causes slight variations in rotational frequency. Recognizing beating is essential because it can indicate synchronization issues or mechanical coupling between machines. Analysts must account for beating when interpreting vibration data, as it can obscure the true severity of faults and complicate trend analysis. In the frequency domain, beating typically appears as two closely spaced peaks corresponding to the original frequencies. If the resolution of the spectrum is high, these peaks are distinct. If resolution is low, they may merge into a single peak that fluctuates in amplitude over time. This variability can make beating difficult to diagnose from stored spectra alone. Real-time observation during data collection often provides clearer insights, as analysts can witness the amplitude modulation directly. Understanding how beating influences spectral patterns is critical for accurate fault identification, especially in environments where multiple machines operate in proximity or where speed variations occur due to process changes. Correcting beating involves addressing the root causes of frequency proximity or mechanical coupling. Common strategies include adjusting machine speeds to increase frequency separation, identifying and rectifying sources of speed drift, and isolating transmission paths between machines. For example, removing a trial weight after balancing or tightening loose foundations can eliminate conditions that promote beating. In some cases, operational adjustments such as modifying control setpoints can prevent machines from running at near-identical speeds. Effective correction not only reduces vibration variability but also minimizes the risk of fatigue and wear caused by cyclic loading. Definition and impact of intermodulation. Intermodulation occurs when two or more vibration signals interact, producing additional frequencies that are the sum and difference of the original frequencies. This phenomenon is common in systems with closely spaced frequencies or where amplitude modulation exists, such as gearboxes and bearings. Intermodulation can generate unexpected spectral components, complicating fault diagnosis and masking the presence of primary forcing frequencies. Analysts must recognize intermodulation patterns, which often include sidebands or low-frequency components, to avoid misinterpretation of data. Understanding intermodulation is essential for advanced vibration analysis, as it provides insights into complex interactions within machinery and helps identify underlying mechanical or structural issues.